Now there's a theorem called Stone's theorem that says that any unitary operator that obeys this kind of property can be written as the exponential of its parameter times some operator, and that operator is known as the generator. And indeed, generators are very important in discussing symmetry, so let's go into a little bit more about that right now. Suppose we have a unitary operator with r values, and most of them are 0, except for one, just the jth one, and the jth one's very, very small. Then we know that when all the parameters are 0, this unitary operator, this transformation, should be the identity. So therefore, when we've got just one very small, if we do a Taylor expansion around that, then we should be nearly equal to the identity. It should be the identity plus some linear term to first order proportional to epsilon j. Now we have a factor of minus I in h bar. That is simply convention, and indeed the convention does change from here to there, so do watch out for that, particularly for plus or minus signs and existence or non-existence of that h bar for when you are looking at other texts. And of course there'll be higher order terms, which will be of order epsilon j squared or higher, so we use order notation to describe those. Okay, now this is a unitary operator, which means it has the property that the Hermitian conjugate is its own inverse, and so that equals 1. And we can expand each of these out. And when we take the Hermitian conjugate, the minus I is going to turn into a plus I, and the gj is going to turn into a gj dagger. Now on the left-hand side here, we have that this equals the identity, and that's true for all orders, for all epsilons. And so therefore, this is true for all epsilon, that these two are equivalent. So the 0th order is in fact the identity equals the identity, so that works. The first order, on the left-hand side, we have 0. On the right-hand side, we have, and indeed there are higher order terms that are also 0 there, and there are higher order terms here that are not necessarily 0. But this clearly shows, since this has to be true to first order, this clearly shows that this thing here in the brackets has to be 0, or in other words, that it's Hermitian, the generator is Hermitian. Being Hermitian, the generators are candidates for being observables, and indeed the very first unitary operator that we met was the time evolution operator, which was generated by the Hamiltonian. And if we look at the units of this, the Hamiltonian has units of energy, and you'll note that since this has no units, this thing collectively must have no units. So this thing here has to have units of h bar. When this had units of energy, then this had units of time, and that was collectively unitless. And so these generators, they can be observables, they can have units just like observables have, and these parameters have to have units. Just like the translation transformation, the parameters had units of length. A generator is discussing an infinitesimal transformation, and of course if we take enough infinitesimal transformations and add them up in some kind of integral, then we should get a finite one. And indeed for additive transformations we saw then building up to a finite one was very easy. It was just simply the exponential. Now clearly this is the first order term if we take the Taylor expansion of this. The interesting thing is that for additive transformations we can get this for extremely large values of this parameter, and it's just simply the exponential. Now our first example of an additive transformation was translations. So translations are going to be of this form. The parameter is going to be a position. But what's the operator going to be? Well, we've got two main clues. The first clue is the units. The second good clue is from classical mechanics, where we saw that the symmetry of a system with respect to translations led to the conservation of momentum. And indeed, the generator for the translations is the momentum operator. This is in fact the definition of the momentum operator. So this is the definition of the operator. The operator is an observable. The momentum operator is a Hermitian operator, as all generators have to be. And so it's actually a physical quantity, and this is the definition of momentum. This is true in classical mechanics, this is true in quantum mechanics, and it's also true in relativity. So this is actually a fundamental definition of momentum, which we've never actually met before. We've only just kind of discovered it as something that was conserved in some situations. And now we know exactly why it's conserved, because if a system is symmetric under translations, and we know exactly what it is. It's the generator of that translation. So now that we have this language of generators, we can start talking very specifically about symmetries and their relationship with transformations. So we discussed that if we have a state and we apply some kind of continuous symmetry to it, then we can change that state, and it's characterized by just applying a unitary operator to it. And we decided it was unitary because we demanded that if we have a symmetry and we apply it to both a state and any other state, then the inner product between those two states had to be the same, and so this had to be 1. However, we've changed the states here, and we've changed all the states, which is why we didn't change inner products, but we haven't changed any of the operators. And if we look at an expectation value, or indeed an inner product of some operator, then this thing here might change, because if I apply my unitary operators on the states here, then this does not have to give me the same inner product that I would have had without that transformation. And one thing to notice here, of course, is that we've got, again, that choice of do we apply our transformations to our states, or we could equivalently decide to apply all our transformations to our complete set of operators instead. Or you could apply transformations to your states and inverse transformations to your operators and end up back where you started. Let's have a look at an example of applying the transformations to the operators for our translation example. So in our translation example, our parameter is a position, and we'll have our position operator. Note the position operator and this position are very different. This is a number and this is an operator. And remember that these translations are just given by the exponential plus for the dagger. Now what do we do about this? Obviously x and p don't commute, so these functions don't commute. However, in assignment 4 we worked out what the commutator of two functions was. If you have some function of the p operator, then the commutator between those two you worked out was just IH bar times the derivative. So we can apply that here. So this way around is going to be equal to that same thing the other way around plus the commutator. And then because the kernels of this, that's just proportional to the momentum operator, and so is that. So these two functions commute, and so in fact the product of the exponentials is just going to be the identity. So that first term is just x, and what's this second term? The derivative of the exponential is the exponential. And the I and the minus i's cancel, the h bars cancel, and then we just have this product of an exponential and the negative exponential, so they go to 1 again, and so we get x plus x. So this x is just the number, and this is the operator. So if I had explicitly made that a 0 all the way through, that might be a little less confusing. And so that x, the operator, transforms to x plus an extra number, which is exactly what you expect the translation to do. In classical mechanics, a constant of the motion came from a time-independent continuous symmetry, specifically of the Lagrangian. But in quantum mechanics, our time evolution is more naturally given in terms of the Hamiltonian. So if we're going to look at how the symmetry changes the Hamiltonian, then the transformation applied to operators, we have U dagger operator U. And so if this is a symmetry, then applying that transformation does not actually change the Hamiltonian. So we apply it to the Hamiltonian, but it doesn't change it. If we pre-multiply by U on both sides here, we get the identity, pre-multiply U, and we show that the commutator is 0. If we take this and multiply by U dagger on each side, we can show this. And so that's each way. And from the Heisenberg equation of motion, we know that if the commutator is 0, then if we were to look at, say, the evolution of the transformation in the Heisenberg picture, we would find that it would not in fact evolve, which is why it's called a time-independent continuous symmetry. Now if we go from here and we expand out these transformations in terms of the generators, and we'll just have one parameter g. G is Hermitian. This is true to all orders in S. The 0th order is just h equals h. The first order is, and therefore clearly the commutator of the generator and the Hamiltonian is 0. And if there's an operator that commutes to the Hamiltonian, that means, say in the Heisenberg picture, it does not evolve at all. Then what we have is that this quantity g, which remember is an observable and therefore can be measured by some measuring device, this quantity g represents some physical property that is conserved. And thus we've got that a time-independent continuous symmetry provides us with a conserved quantity, the generator.